Today we'll just be covering conditional expectation and variance, which are traditionally pretty tricky. So, bear with me here and don't feel bad if you need to, pause the video or replay any parts of it. So yeah, let's just jump right into it. So the conditional expectation of a random variable x given the event that big Y equals little y is defined as follows, where we just sum over the product of x and our conditional PMF for all the possible values of x in the discrete case, so that's this guy here, or where we integrate over the product of x and our conditional PDF over the range of x with respect to x, right, in the continuous case. Now, you can think about this as just taking the expectation with respect to a conditional distribution. I know our notation is a bit weird, but really that's all this is. And because that's all this is, you can expect the usual linearity and independence properties to hold, right? So if you recall our example from the joint distribution video, right, we found that the conditional PDF was 1 over x for y in the open interval 0 to x, this guy right here. So directly following our definition in the continuous case that we just presented up here, we find that this is our conditional expectation, right? The integral is pretty standard, so I'm not going to explain that here. But really, right, notice that we're differentiating with respect to y, right? Because we want the expectation of y given big X equals little x, right? So other than that, there's another thing I'd like to show you here. So notice that the law of the unconscious statistician still holds, right? I'm not worrying about my y squared. I'm just throwing it in there. And, we're chilling because this is the nature of it being an expectation, right? And lastly here, this is pretty important, but it's easy to get confused about this, but you'll see that whenever I'm conditioning on big Y equals little y or big X equals little x, our conditional expectations are really just a function of our conditioning variable, right? There's nothing else there, so it's just a function of the conditioning variable. So in this example, it's pretty clear, but remember that for the general case as well. So for any two random variables, big X and big Y, the conditional expectation of big Y given big X is defined like so, where we just make this function, h of x, equal to our conditional expectation from the last slide, right? This guy right here. And then when we plug in big X, our random variable, we get the conditional expectation of big Y given big X, which is a random variable, right? Because of the properties of functions of random variables. So now the law of the total expectation is only possible because of this definition, right? Since the expectation of big Y given big X is still a random variable, not a constant, not a function like in the last slide. It's a random variable. And because of that, we can take, the expectation of the expectation. So if that's not clear, just pause here for a moment before I actually get into what the law is. And, rewind that, re-listen to the last slide, and make sure that the difference between this conditional expectation and the conditional expectation on the last slide is clear to you. So here I'm just going to prove the discrete case, right? I've left the continuous case as an exercise, but really it's the same thing. You're just moving around integrals instead. And I want to draw your attention here. I'm just taking the expectation of my of my random variable with respect to big X, right? Since the expectation of big Y given big X is a function of big X, not of big Y. Don't forget that, right? That's a common pitfall. But that's really what I'm doing here. And then from there, I'm just expanding and rearranging the sums, right? So this first equality comes directly from our definition in the last slide. And this second one comes directly from the definition of conditional probability. And this guy is just definition of marginal probabilities. And then we're done. We're proved for the discrete case. The conditional variance of a random variable x given the event that big Y equals little y is defined as follows, where we just sum over the product of x minus our conditional expectation squared and our conditional PMF for all the possible values of x in the discrete case. So this guy right here. Or where we integrate over that same product, except this time it's our conditional PDF, over the range of x with respect to x in the continuous case, right? This monster right here. Now, you can think about this just like we did in the conditional expectation, right? We're just taking the variance with respect to a conditional distribution, which is why, the regular expectation of x that would go here is replaced with our conditional expectation. And that's also why you can expect the usual properties of variance to hold. Now, maybe most important of which, for you, is the fact that we have this easier definition here, right? Which is the proof is virtually identical in the unconditional case. So notice all I'm doing is letting my conditional expectation, e of x, given y equals little y, be some constant c, because that's what it is. And then from there, I use the fact that our initial definition, both of them, are really just expectations hidden in plain sight, right? And then I'm just rocking with the linearity properties of expectation, and we're done. If we define the conditional variance of big Y given big X as a random variable, just like we did in the conditional expectation slide, by making a simple function h of x, that's really just the definition of conditional variance in this case, right? Then the expectation of that random variable is given by this following guy right here, right? Where I'm just plugging in our easier definition from the last slide here, and then I'm using the linearity properties of expectation to go from this guy to this guy. And now, this doesn't really help us that much, but notice that the variance of the conditional expectation random variable from 2 slides ago is given by this guy right here, right? Where I'm just using our easy definition and then again the law of total expectation to go from here to here. So now you might be like, okay, wait a minute, these guys are pretty similar. And you'll notice that if we add both of these terms, we get our law of total variance, right? That the sum of these guys is just our variance of x. And, you might be like, what's this or the law of total expectation really used for? It seems kind of arbitrary, abstract stuff. But, other than the fact that you'll definitely be tested on one of these guys, they will save you when you have the need to find, some really weird variance or some really weird expectation. It's kind of like in conditional probability when you use Bayes' theorem or some complement stuff. It's useful when you need to rewrite probability in terms of stuff you know already. So keep that in mind in a moment when I show you the practice problems. So here I've left the practice problems, and this first one might be a bit tedious since it's discrete, so you're just adding stuff up. But it's worth doing if you think you'll be tested on discrete stuff. Otherwise, 2, 3, and 4, these guys are really valuable practice. But yeah, either way, feel free to leave any questions you have in the comments. And thanks for watching. I'll see you guys next time.